Hello, good afternoon. Thank you all for coming. My name is Krzysztof, and I will talk about the reactive programming using the RxSwift library. The theme of my talk would be how little do we know about the observable the moment that we are subscribing to it. It's going to be a story of one bug hunt and three big questions. But before we even start, let's meet the hero of our story, Alex. Alex is an iOS developer working on a popular app. Alex is passionate and dedicated. They keep their finger on the pulse of the community. They use the latest and greatest tools available. They always seek the best solutions. Each day, they try to write the high-quality code and provide the best experience for the users. And one day, Alex has attended the mobile development conference, just similar to the one that we are here right now. And they had seen a talk about the new idea of writing applications called reactive programming. The speaker was saying that it's like an awesome way of writing asynchronous code in a unified way. So instead of using like the whole pantheon of patterns like target actions, completion blocks, delegations, and so on, you're just using always the same pattern, and the pattern is highly composable, and it's called the observable. And it's going to make your app easier to maintain, and it's going to make your app easier to reason about. So Alex found this paradigm fresh and fascinating, so they evangelized it among their company, among the developers on their team. And when the time came for their app to be like partially rewritten, the whole team agreed to use the RxSwift as the core part of their architecture. And everything went smoothly, users were happy, and I wish that was the end of the story, but well, as you can imagine, it never is. One day, the company started receiving numerous reports of a bug. The bug was happening on the screen, one of the many screens that presented some data to the user, and it was as follows. When the user pushed the refresh button, nothing happened. The spinner indicating that something is refreshing just kept spinning indefinitely. It was never finishing the actual refreshing. So the app didn't crash. There was no stack trace. And this is the type of bug that is, from my perspective, most commonly encountered when using reactive programming. I mean, the data is just not propagating properly. There's no crashing, but the data is not propagating. So Alex quickly found the actual lines of code that are responsible for handling this refreshing logic. So let's go through them. First, the refresh data method is being called on the data provider service. And it returns the observable that emits the refresh data. We are subscribing to this observable by providing two closures that define how the events are consumed. If everything succeeds, the update method is called with the new data. And it's responsible for populating the views with the informations. If anything fails, there is an error. We are checking what the type of the error is, and if it's of type that exposes the user-friendly message, localized message, that explains the reasoning behind the error, we are showing this message to the user. Lastly, to ensure that subscription is being cancelled when the screen is being deinitialized, we are adding the subscription to the dispose bag. And on the first side, the code is pretty simple. I mean, what can go wrong with such a basic usage of RxSwift? The first question that Alex asked was, maybe the self-reference inside the subscription closure is nil at the moment that event arrives. Then, I mean, the update will be called on nil object, so nothing will ever happen. That would explain the lack of refreshing. But is it really possible in this situation? To answer that, let's look at what happens under the hood when you are creating an observable and then subscribing to it. It will help us to see what are the possible traps waiting for us along the way. So, when you first create an observable, there's an object allocated in the memory. The actual type of the object depends on what operator did you use for creating the observable. But it's always an object that can generate events, and it's always an object that is a subclass of the observable type. So here's the just object. It's a source of the events that we are working with. Then you can start shaping the flow of events by adding some more operators. Each time you do that, there's another object added to the previous observable. So here we've just added filter. And now we're adding map. And now the observable is of map type. Internally, as you can see, we are creating a composite object made of layers, right? And each layer is a different observable instance of its own type, and each of those instances keeps the reference to the previous one. So they together make something like a chain, okay? But from the perspective of the client, all you can see is only the latest, the most outer observable. So the underlying structure is completely opaque. It's hidden under the observable type. You cannot know whether the observable is composed of like only one event generating layer, or is it like composed of hundreds and hundreds of layers. The methods that it exposes are always the same, so there's no way of knowing how huge or complicated the observable is from the outside. But there's more. Many of the operators take closures of parameters, and those closures store the references to everything that's been used inside them. These references are captured at the closure creation time, and that means that many layers of this composite observable object may actually keep references to the environment, which makes the actual memory graph even larger. So the object is actually even larger. And there's still no way of knowing about it. Now let's see what happens when you call subscribe on the observable. There's like a cascade of new object creation, okay? These objects are called sinks. Each of them contains the actual logic required to perform on the events coming from the previous sink. So this is the actual logic of the operator. The filtering is in the filter sink, the mapping is in the map sink, and so on. The initial sink is working on the events generated by the initial observable and then passing to the second sink. And the second sink is doing its work and passing to the third sink, and so on and so on. So this way, the events are going through the whole sink chain, and the whole logic that you have expressed is executed eventually. Of course, to perform this logic, the sinks must have all the tools. So, for example, if there is like a filter sink, it has to have the filtering closure. It usually means that those closures are passed into the sinks, and sometimes it means that the observables are no longer required after subscription. Sometimes they're just disallocated. This is all there is. And sometimes they are still kept for different reasons, but this is like the thing that depends on the particular operator implementation. The important thing is, from this moment, the sinks are the main guys. Like, these are doing the actual work. Also, when we are calling subscribe method, we are providing some instructions to be executed when the particular event is being received or the particular state of the subscription is being like reached. And the logic is wrapped inside the object called the observer. And this is like the final thing. This is the last piece of the chain, which means that it's the final receiver of events, the opposite of the generator. So this is all there is about sinks, but there are another pieces to this puzzle. The moment that you subscribe, there are another objects created called the sink disposers. And sink disposers are objects that implement disposable protocol with only one method called dispose. And this method contains the logic required to stop the subscription and clean up the resources, okay? So sink disposers are also structured in a chain, but the chain goes the other way around. So sink passes the information from the top to the bottom, from the generation to the observer, and the disposers passes the information the other way around, from the outer layer to the first layer. And sinks and sink disposers create a lot of reference cycles, which keeps the subscription indefinitely. So when you start working with RxSwift, it's like a common mistake to think, once I let go of the dispose object returned from the subscribe method, the subscription is just disallocated. No, it's not. I mean, it's just kept alive by the reference cycles. Automatic reference counting cannot work with that, right? There is, however, a way to break the cycle, and it's related to the object that's been returned from the subscribe method, to the disposable. This is disposable that's returned from the subscribe method is actually the last sync disposer in a chain. So this is returned under the disposable protocol, but it's the sync disposer behind the protocol. And when you call dispose on this sync disposer, on the disposable object, it nills out the reference to its sync, and then it tells the sync disposer above it, do the same. So after a while, after 2 steps, all the sync disposers in a chain, they just cancel the references to the syncs, and there are no more reference cycles in this graph, so everything can be deallocated. So this is how it works. The subscription ends, everything is deallocated. The dispose method is therefore the only way of releasing the references carried by the observable and finishing the subscription. It may be called externally on the disposable object that you've just seen is returned, or it could be called internally when the .completed or .error event is received. Is working the same. So this is like life cycle of subscription. This is how it lives and dies, and there's like, you can see no magic to it, only like a web of references that keep it alive. And while we at the references, let's briefly talk about the last element here. The observer is usually created providing the closures that are describing the job to be done when the events are received. So those closures can catch another references from the outside, and they usually are, and usually very, very often they're actually catching the reference to self, because we are subscribing usually in some object scope, the scope that is actually using the data from the subscription. So all those sync and sync disposer, they don't really add much of references from the environment to the whole structure, but the observe closure very well may. Okay, so this is like the whole picture. Let's bring it all together. There are 2 properties of the RxSwift API that make it painfully easy to create memory management related bugs. Okay? And firstly, it uses closures extensively, and those closures might have a lot of references, possibly to things from the environment. And secondly, the subscription is kept alive by itself. So it contains reference cycles between sync disposers and sync. It will be never deallocated unless we make it deallocate. There are 2 main types of bugs that can originate from a wrong memory management in RxSwift. First, the memory may just leak. I mean, if something is not deallocated properly, it's leaked. Secondly, the lifetime of some objects might be extended. And this is just an opinion, but from my perspective, the memory leaks are actually the less dangerous of those 2 bugs. Because, okay, it's wrong to leak memory, but if it doesn't make any other effects, I mean, there's a lot of memory, that we have to leak a lot of it to actually crash the app. But if you extend the lifetime of some object, it's very often basically like having your app in the undefined state, because there might be a lot of code written under the assumption that the object does not longer exist. It doesn't receive any events, it doesn't change any shared state, it doesn't, well, execute any instructions. So combine that extended lifetime that you don't expect with the asynchronous nature of the reactive programming, and you might find yourself having some really weird bugs. Fortunately, there are 3 simple rules to follow to minimize the possibility of any memory-related bugs in reactive programming with RxSwift. First, always dispose your subscriptions. What method you choose for disposing is up to you, it's up to the situation you're working with. You can just drop them into the dispose bag, you can use the serial disposable, you can keep the reference to the disposable returned from the subscription and call the dispose method, well, explicitly. Whatever you choose, ensure that you know when your subscription finishes. I mean, like, don't be surprised by that. Make it finish the moment that you want it to finish. Second, avoid strong references in closures if it's possible. especially the strong reference to self. I cannot emphasize this enough, because this ties the lifetime of your objects to the lifetime of the observable and subscription, and it's very rarely what you really need, okay? You very rarely want this connection, this coupling. Also, when you do that, prefer weak references over unknown references, because weak references, they require you to handle the possibility of object being deallocated. You have to just write the logic for that. And the unknown references are found only if you are if you can completely guarantee that the life cycle of the captured object is longer than the life cycle of the subscription. So the one common example that you can use unknown references with is when you just dropping the subscription into the dispose bag from the same scope. Then the moment that things will get deallocated, the dispose bag will get deallocated, the whole subscription will get deallocated. So there's like no possibility, it's totally impossible for the self to not be alive at the moment that event arrives. Third, do not pass instance method as operator parameters. Like instant methods, they keep the strong reference to self. They always do. It's like the implicit first parameter, but you cannot see that from the usage. Like it's just foo. It doesn't say anything like self foo, right? It looks just like a function. So that's why you should always pass a closure. Even if you want to catch the strong reference, always pass the closure, because then at least you are expressing that there is self captured along the way. Which brings us back to Alex and the backhand. So looking back at the code in question, we can see that there is no possibility to for self to be nil before the subscription finishes because of the dispose bag. Actually, Alex might as well just use a known reference and it will be okay, just for the readability sake, but it doesn't solve the problem that the screen is not refreshing. So there was another idea that Alex had. Maybe it's a threading issue, okay? So after all, the update method is working on some UI elements, and calling the UI elements from the background thread, I mean, any thread that's not a main thread, may lead to some strange and undefined behavior, sometimes crashes, but sometimes just glitches. So maybe the lag of screen update is just a glitch. But how can we know which thread will the particular part of the observable stream execute on? I mean, you cannot just ask the observable for it. There are, however, some simple rules to follow to understand what's going on. But first, let's quickly refresh the concept from the RxSwift called schedulers. So schedulers are the abstraction over various methods of performing work in particular context, which is like a very loose abstraction, okay? We'll go through examples in a minute. So they are just like defining the where, the when, and the how the work will be actually executed. Well, many things can be seen as part of work performing context, and this is actually like expressed in the basic scheduler protocol. This is like the protocol of the basic scheduler. It just takes the state, which is like the argument, and the action, which is the actual work, that takes the state as the first parameter, and it's up to the scheduler to decide when, how, when will the action closure be executed, passing the state as the first parameter. And so if you're writing a custom scheduler, which you can, I mean, there's nothing stopping you from that, you can basically do whatever you want here. I mean, like you can make a scheduler that doesn't work at all, or it doesn't work on Mondays, for example. I mean, you can do whatever you want. In practice, however, schedulers are usually most often used as wrappers around the already existing mechanism in the API, the Cocoa API, like threading and queuing, operation queue, and dispatch queue, and so on. Let's see some examples. The main scheduler is for executing the work on the main queue. So when you ask it to do the job, it first checks whether it's already on the main queue, If it is, it just does the job right away. And if it isn't, it just uses the .async method to pass the job to be done in the main queue. The serial dispatch queue scheduler is very similar, but it's working on a non-main dispatch queue. I mean, internally, it just creates the serial queue with the parameters that were provided by the client in the initializer, and then it always passes the work to be done to this queue using the .async method. And the operation queue scheduler is doing something very, very similar, but using the operation queue. So you are providing it with the operation queue through the initializer, and then it simply wraps the job into the operation. It's block operation, it's a system type, and then it's adding it to the operation queue. So this is what schedulers do. They execute job. And there are many, many more schedulers defined in RxSwift, but I mean the idea is pretty the same always. So they have different properties and abilities. Some can execute the job in like a delayed manner, and some can do it repeatedly, so we just give it something once and it repeats the job. I mean, some others are not doing anything, any job, unless like explicitly say, please start the job now, okay? But the important thing is that all the thread switching, all the thread logic in RxSwift is wrapped inside the schedulers. There's a whole group of operators that require you to pass the schedulers when you create them, okay? And what they do with the scheduler, it depends on the actual operator, but they do require you to pass them some, well, tool to do the job on. Other operators are just scheduler agnostic, which means you do not pass any information about the job execution context to them. They just don't care. And last but not least, there are also some scheduler defining operators, there are two of them, which are used for defining the operation context for the other operators in the chain. To make sense of it all, let's go through a simple example. So here we have an observable that is composed entirely from the scheduler agnostic operators. So there is like no information in this chain about the execution context. So all the operations will be executed in a thread that the subscribe method was called on, because this is like the only thread that there is. So this is the observable work thread. But you can change that using the observeOn operator. So observeOn defines what scheduler will be used for execution of all the operators down the road. So the observable is always single-threaded because it's a sequence of events. So because it's a sequence, there are only one event at a time. So it's single-threaded. And observeOn is basically a way of switching the thread for this observable along the way that the event is going through. One interesting thing to notice is that the operators above the observeOn, they are still being executed on the subscription thread. So observeOn only changes anything for the operators down the road, never for those before it. And you might use as many observeOn operators as you want. I mean, the semantics always stay the same. It always changes the execution context for the operators following it and just does nothing for the operators before it. As you can see, using the observeOn, it's just like plain impossible to change the first execution context, the generation thread. So this is why there is another operator dedicated just for that, and it's called subscribeOn. And subscribeOn specifies what scheduler the subscription logic will be executed on. And the generation of an event is part of the subscription logic here, so it defines the initial scheduler, the first execution context. And because event generation is like a single step, so changing it along the way multiple times doesn't really make any sense because it happens only once for each of the events. So it doesn't matter how many times you call the subscribe on, only the first one matters. Other ones are just like plain ignored. They just don't do anything. Also, if you are providing the scheduler to run the generation on into the generating operator, like explicitly, then it just ignores any subscribe on calls later because the scheduler is already defined. So here we are using a variant of the just operator that actually takes the scheduler, and now you cannot do anything about that. It's like it's just subscribe on, doesn't do anything. So these were the rules for keeping track of the execution context for the scheduler agnostic operators. But what about the scheduler using operators? The situation becomes a little bit less clear there, a little bit more mugged. First, let's divide those scheduler using operators into two groups. Some of them are using the schedulers for the generation of events, and others are using it for the internal work. And those that are using schedulers for generations are way easier to reason about, because you can almost always safely assume that they will be passing the events further in the execution context used for the generation. And the documentation of RxSwift library even sometimes says that like explicitly, scheduler to send elements on, okay? But operators using the schedulers for the internal work have way less guarantees. Sometimes they pass the events in the execution context that you've been given them to make the work, and sometimes they pass it in the execution context of the previous operator. I mean, basically you just cannot assume anything about them. And to make things harder, there's also nothing preventing the observable from changing the execution context from event to event. The simple example is a merge observable. So here is a merge observable that is composed of two observables working on different execution contexts, on different schedulers. And there's nothing preventing you from writing code like that. I mean, the types must match int and int, but the scheduler doesn't have to match. So the result is that this subscription closure is, well, sometimes executing in the red scheduler context and sometimes in the green scheduler context. Well, it depends on the timers. This can lead to some nasty bugs. So how can we protect ourselves? First, it's good to understand what's going on. So read the documentation to learn what are the properties of the particular operator that uses the scheduler. It might state explicitly in the documentation what does it use the scheduler for, and sometimes that's enough. I mean, you just then know that it's guaranteed because it's in the documentation. And if the docs are not explicit enough, read the source code. The source code for operators is surprisingly simple when you just filter out all the infrastructure around them. So you might learn a lot along the way. And if you are still in doubt, ensure the execution context with the observeOn operator. There's like no penalty that I know of for using the observeOn many times, apart from the performance issues probably. I mean, if you are using it too many times, there could be some performance issues. But I mean, performance issues are still a little bit better than the upcrashing, so sometimes it's a worth trade-off. And finally, you can use Rx Cocoa traits like driver or control property, because they are guaranteed to work in the main scheduler context, okay? They are just designed to work with the UI elements, so they will never use background thread. You can be pretty sure about that. So going back to Alex and the mysterious bug, as we have seen, there's like no way of asking the refresh data observable what is your execution context, so Alex decided to choose the safest option and just add the observeOn operator before subscription. However, it doesn't stop the bug from happening. So what else could go wrong? There's one more idea that Alex had. What if the observer closure is like never executed because the events is never received? So how can we know whether the observable is emitting event? How can we know whether it will ever emit any event? Well, there are many possibilities for the events to not being passed to the observer. The subscription might end before they are emitted. There might be some bug in the implementation of the generation logic. Or the observable stream might be defined in a way that it just filters out some class of events and they're just not being passed down the road. But as usual, when working with the observables, there's no way of knowing. We need to go a little bit deeper with our analysis. But let's start with basics. The observable generates a sequence of events, and there's a basic set of requirements that each of those sequences must keep. So it always consists of 0 or more next events, and the event that closes the sequence, that is the last element of the sequence, is either completed or error. And anything emitted after the sequence has finished is just ignored because it's incorrect. It doesn't follow the guarantees of the observable. Okay, so this is the base on which multiple different possible communication protocols of the observable are built. So these are not the Swift protocols. This is nothing related to that. But the communication protocols of the observable. So the communication protocol, as I can see it, is just like a structure of the sequence of events. And because the structure of the sequence of events that will be emitted by the observable changes the way you can use it, changes the way you subscribe to it, it's a very important thing to ask yourself some questions about what possible events may be emitted and in what relation to each other. First, very basic question is whether the sequence of event will ever finish. So will there ever be completed or error event emitted? And if it does finish, and we are absolutely 100% sure it will finish always, we can basically ignore the whole memory management. I mean, why not? I mean, this is the code that I would not write, but it's still a valid code if you can prove it, that the subscription will 100% end because there will be a completed or error event emitted by the observable. Here, however, is just like non-finishing observable. So if it's not finishing, then it's our job to ensure that the subscription will be disposed. So the communication protocol of the observable, finishing or not finishing, actually defines whether we are using the disposable object or not. Another question we may ask is how many events can we expect from the observable? I mean, is it like something that lasts for a long time, or is it something that is closing after the first piece of data? And if it's like a one-off sequence, which means it contains only one piece of data, then each time we want to fetch the new data, for example, we need to create new subscriptions. So we're just making like a series of subscriptions. So in a way, here, we are just pulling the data using the observable as a tool whenever we want it. But if a sequence is a long one, which means there will be multiple events, then it could be the observable's job to push the data to you. So then we are subscribing only once, and we expect we will be given the information at the right moment in the future. So it's like the Hollywood principles. Don't call us, we call you. Again, because of the communication protocol that is invisible, we are subscribing to observable in a different way. Another question. How does it start emitting? What about the first event? When will it be emitted? How it will be emitted? One possibility is that the moment you subscribe to the observable, it immediately and synchronously calls the observer closure with the first piece of data. And this is, for example, the logic that behavior subject has. And sometimes this is just what you need because you want to have the first initial value after you subscribe. But sometimes you are subscribing in a moment that you are like, not ready to handle the update yet. So then you have to skip the first piece of information. Sometimes the opposite situation occurs. The observable doesn't push you the first piece of information. Then you have to, for example, cache it somewhere in the other object under some other API call and expose it to the client so that it can propagate, for example, the data to its UI and then listen for the updates. And this protocol is, for example, been kept by the publish subject, which doesn't give you the last data, only the following updates. And another thing that is very often a source of confusion is whether the observable caches the events or the fruits of its job, let's say. The canonical example is about network request. So imagine you are exposing the observable that causes some huge network request to happen. If it's not caching the results, then each time you're subscribing to it, there is another network request given. So that could be a huge waste of resources, but also you are getting the fresh information each time. But then you can use the share operator, share replay, to cache the events, and the request call will be done only for the first time you subscribe to the observable defined like that. No resource waste will be done on the second subscription, but also we'll get the old data, okay? So the underlying communication protocols changes what you get. And there are many, many more questions one can ask about the protocols. For example, the error types are part of the invisible observable communication protocol, how the events are related to each other. For example, maybe the observable finishes, but finishes only in 1,000 years, so basically it doesn't for you. The point is not to enumerate all those questions, all those issues, but to see how important the protocols are to know about when you are just using the observables. So how can we prevent ourselves from getting lost in this like whole maze of the hidden communication protocols? So the best thing is to shine some light on them. And there are multiple ways to do that. First one is to expose the protocol in the type system, and this is something that RxSwift and RxCocoa is already doing. There is a number of traits in RxCocoa that are keeping some communication protocols properties. For example, driver, signal, and control property, they are all guaranteed not to fail. This is a guarantee. Also, they have some caching properties, changing from one another, and also they are guaranteed to use always main schedule, as we said. So, and there are more traits in RxCocoa with different characteristics. And also there are more traits in the core RxSwift library. For example, there are single, completable, and maybe types, and each of them is actually like the whole purpose of existing of this type is to expose the protocol, the communication protocol, concerning how many events will be sent, whether it will be finishing or not. And there are also many more traits defined in RxSwift. So using traits, whenever you can, makes the protocol way easier to understand, but sometimes there's like no traits that fit your situation that you can use. So you might write your own wrappers, that's fine. Or you can just use the plain old comments and documentation to explain the protocol of the particular observable to other developers. For example, here's like a complicated domain logic observable. It's non-trivial, but it's well-defined. So there's a lot of things that are guaranteed, okay? And you can just write them down. You can just explain them. And anyone that will use this method will really feel good about you, okay? It will really like the one guy or girl who wrote the comment above. And often when you are working in a on a big app, in a big team, there are some common patterns and conventions that arrive, and the communication protocol, in particular, application layer might be part of those conventions. Then even if the actual protocol is somewhat complicated or difficult to understand, the whole team understands, okay? The whole team is just know how to use the API and how to write new types using exposing this API. Example. Here is the part of the service that provides data for view models. And the team agreed, I mean, it's like a convention, that the best way is to expose two methods giving you observables, okay? The refresh data method is not giving you data, it's just causing the refresh and telling you about whether the refresh succeeded or errored, okay? That's all. It's a one-off, it's finishing and so on. And then there's another observable, data observable, that gives other guarantees. It will never error out, it will never complete, but also it will give you updates of data, so you can just subscribe once and use it as long as you want, okay? And if you agree with your team, for example, that those two methods, I mean, they might be good for you, they might not be good for you, but any convention is good for your team as a whole, everyone agrees, then you can just write your services and other services in this way and everyone will understand, although the actual logic is not trivial. And the last thing, the last method of dealing with protocols is to limit the scope of the observable, so that number of places influenced by the protocol, by the changes in the protocol, by the characteristics of the protocol is limited. So the potential bugs are also limited. And there's one concept that I found extremely useful when thinking about the limiting scope. It's called code distance. It's not like very well defined, but it's pretty intuitive. When there's an action in the code, what matters is the distance at which the action causes some reaction. So in other words, it shows whether we keep the relationships local, the coupling local, or if we allow some things that are conceptually unrelated to influence each other. And I like to think about the actual code distance in terms of the app architecture. So if the change in a network layer is like not visible anywhere in persistence or view models, but it influences the view layer, it means there's a long code distance relationship here. And there is one pattern that I've grown to dislike that really uses, that like lives on those long code distance relationships, and it's called notification center. However, if the change in any layer can be seen in the neighborhood, somewhere nearby, it means that the logic is kept on the short code distance. So, for example, if a change in the observable protocol in the network layer affects the services layer or the persistence layer, it indicates that the code distance is short. And well, there's like no universal way I can tell you this is how you shorten the code distance in your app. The rule of thumb is to keep the observable in as small scope as possible, because it will help you reason about what causes the event and what are the guarantees and properties of the events and what effect does the event create. In the meanwhile, Alex has discovered and fixed the source of the bug. I mean, you have probably maybe spotted this as well. So let's see what happened. So the problem was in the on-error closure. And it's very closely related to the code distance, the last thing that I've been talking about. So one of the team members, when working on the network service, just plain forgot to ensure that all the errors that are thrown, they do conform to the reasonable error type. So there was like nothing wrong with the subscription code. I mean, it was fine. The fix was to do it somewhere else. So that's the end of the bug hunt and the end of our journey. And this very end, the last thing I would like to say is to encourage you not to get like scared by all these questions and possible problems that we've been seeing today and thinking about today. RxSwift is like a very nice tool for simplifying the asynchronous programming. And all those problems, all those questions, they also do occur in other patterns, completion blocks, target actions, and so on. So they're just hidden there. And actually, I think that in RxSwift, it's actually easier to spot them and to prevent the problems before they happen. So thank you very much for your time. It was a pleasure to talk to you. If anything was that I was showing was of interest to you, don't hesitate to talk to me. And for everybody here, have a great afternoon. So thank you.